bunch of them. There's no way you're going to finish them tonight, but just consider this a multi-day worksheet and finish them all off, certainly before our next exam, which is a week from Monday, where you will see those syntheses come to life in a more critical way. All right, so that's it in terms of alkynes. I want to, before we start spectroscopy, do this very short chapter, which is chapter 11, I believe. Yes, it's 12 is spectroscopy. No, this is chapter 10. Right. Keeps changing the chapters around. 11 is what we're going to come back to. We're going to finish the semester with 11. And I promise you there are no new reactions in chapter 11. So after we do 3 or 4 more now, we're done learning new reactions. Chapter 11 is all about how a lot of these reactions occur with alkyl halides. So alkyl halides is the subject of chapter 10 and really 11. But 10 introduces these as a functional group. The key thing about an alkyl halide is the polarity of the carbon-halogen bond, where the carbon has a small delta plus charge, the halogen has a small delta negative charge, depending on the electronegativity difference between the two. We've already done a lot with alkyl halides during the course of the semester in terms of making alkyl halides, preparing them, synthesizing them, whatever you want to call it. We saw that you could take an alkane, take a halogen, shine some light on it, and you will get alkyl halides. The problem here is that you typically get multiple products. You might get monobromo or monochloro, dichloro, trichloro, and where the halogen ends up can be problematic to control depending on the alkane that you start with. More reliably, in the alkene chapter, we saw that if you take an alkene, you can turn this into an alkyl halide in 2 ways. You can add halogen to it, either chlorine or bromine typically. Fluorine works, that's usually explosive. Iodine will work, but very slowly. And what you end up with is the dibromo, in this case, or the dihalo compound. Which will always be a trans or an anti-addition of the 2 halogens because of the formation of the intermediate, which is the bromonium or the halonium ion, bromine or chlorine, which kind of bridges one side of the carbocation and protects the other. We can do the same reaction with a hydrogen halide to add only 1 halogen. It's done there. There. By the way, I should say here, you'll get this one and the enantiomer. So there really will be 2 products of that reaction. And you realize that depends on what the question asks for. With the HX addition, you're just going to end up with the halogen and the CH3 will be on the same carbon. And in this case, that's the only product, since there are no chiral centers in there, there are no enantiomers. But you will get the X attacking from both the top and the bottom. So you get both possibilities there. If there was another group on the ring which would make that a chiral center, you would get a mixture of that, and it's an antimer. And the last way of doing it is the new way, which is introduced in this chapter, which is, let me use a nice symmetrical one for now. Take an alkene and treat it with NBS and shine some light on it. So we're shining light on it. That immediately tells us this is probably some free radical mechanism. What's NBS? Anybody remember? You've seen this once before. It's N-bromosuccinimide. I don't care about that. You just need to recognize it as a reagent and realize that it is effectively equivalent to Br2. It is the compound that decomposes slowly and releases Br2 in the solution. It has solubility advantages because it's more soluble than bromine would be in most of these reaction conditions. NBS looks like that. And again, you don't need to know that, but you should know when you see NBS. It's the way of adding bromine to something conveniently in terms of solubility, and also making sure that there's never a lot of bromine around because it releases it slowly. And that's important here because you only want the monobromo product in this thing, and you don't want a multiple bromination to happen. And what you end up with is interesting. You end up with that compound. We keep the double bond. So this is not like the addition of Br2 to a double bond, even though that's what it would be. The fact that we shine light on it means it goes to a free radical mechanism. That means the bromine is going to break apart to Br dot. The Br dot's going to look for hydrogen to grab off the compound. And the most accessible, easiest to remove hydrogens on this compound are these. Those are referred to as allylic hydrogens. They are hydrogens on a carbon which is adjacent to a double bond. Those are even easier to remove than tertiary hydrogens. Why? Well, what do I get when I remove that? The intermediate that this reaction goes through would be that. And why is that a stable intermediate? It's a primary free radical. That shouldn't be terribly stable at all. What stabilizes this free radical? Back to the second lecture, your go-to word, resonance. Resonance structure. Not very good at drawing this resonance structure. I learned last time. Drawing resonance structures with free radicals, but it's a resonance stabilized free radical, which moves the dot over there, which means it's the easiest hydrogen to pull off, and therefore that's the compound that you get. An allyl group, by the way, just in general terms, is anything that has this